Welcome. In this explainer, we're going to pull back the curtain on artificial intelligence. We're going to unpack the core engineering logic behind how an AI actually learns to see, and we'll do it using a powerful analogy you won't forget, the assembly line. Okay, so here's our game plan. We'll kick things off by looking at the massive data problem that images present to a computer. Then, we'll see the incredibly clever tricks engineers use to solve it, build out the full assembly line, and finally, we'll look at the actual blueprints for some of history's most famous AI models. So, to really appreciate the genius of the solution, we first need to get our heads around the true scale of the problem. What an AI faces when it looks at what we think of as a simple picture is anything but simple. You see, a single standard-sized image isn't a picture to a computer. Not at all. It's a grid of numbers. And in this case, it's over 150,000 of them. That is just an enormous amount of raw data for any system to try and make sense of.
And that right there is the core engineering challenge. How on earth does a machine find a meaningful pattern, like a cat, in this absolute sea of pixels? And how does it do it without just memorizing that a cat's ear is always at pixel location 105, which of course it never is?
So to crack this nut, engineers realized they couldn't just throw more raw computing power at it. They had to be smarter. They developed this brilliant technique to shrink the data, to squeeze out all the noise, while making absolutely sure they kept only the most important information. And this first tool on our assembly line is called max pooling. Now, the concept behind it is just beautifully simple. In any given neighborhood of pixels, we're just going to pay attention to the one that's shouting the loudest. We keep the strongest signal, and we just let the rest go. So imagine this grid is the output from one of our feature detectors. Maybe it's one that's trained to look for the gentle curve of an ear. The higher the number, the more confident it is that it found something. This is our raw data. The process really couldn't be simpler. We're going to slide a little 2x2 window across our grid, and for each little neighborhood it lands on, we ask one simple question. What's the single biggest number in here? That's the only one we're going to keep. All right, let's actually do it. In that first top left spot, our window sees the numbers 1, 3, 5, and 6. Well, the strongest signal, the one that's yelling, "Hey, I think I see something important," is the 6. So that's the only value that gets to move on. Now we just slide the window over to the top right, and here the number 9 just completely dominates that whole area. It is the clear maximum, so it's the only piece of information that gets passed down our assembly line from this section. Now we just keep repeating the process. For the bottom left window, the max value is a 4. And for the bottom right, the strongest signal is clearly that 8. Simple as that. And would you look at that? This shows the result of our work perfectly. We started with 16 numbers, and now we're down to just 4. We have literally thrown away 75% of the data, which dramatically cuts down on the work the computer has to do, but, and this is the key, we've preserved the strongest, most important feature signals from each little region. Now, this simple trick gives the AI a kind of superpower. It's called translation invariance. And all it really means is that the model stops caring so much about exact pixel locations. It learns to recognize a beak, whether it's right here or shifted 1 pixel to the right. It's looking for the feature in a general area, not some precise spot. So let's zoom out from that one tool and head to the main factory floor to see how it fits into the bigger picture. And what you'll find is that nearly every successful vision AI is built like a funnel. This funnel design follows a very deliberate engineering logic. At the very start of the assembly line, the data is wide and shallow. This lets the AI search for simple things like edges, curves, and colors across the entire image. But as the data moves along, it gets squeezed, becoming narrow but much, much deeper. This allows the AI to combine those simple features into far more complex concepts, like an eye or a wheel or a specific fur pattern. So this is the absolute core logic of the funnel. As the spatial size of the image, its height and width, gets smaller from all that pooling, we actually increase the number of feature detectors or filters. Now, why would we do that? Well, think about it. The concept of a vertical line is really simple. But the concept of a cat? That's incredibly complex and abstract. You need way more specialist filters working together to identify them. This whole funnel idea isn't just a convenient analogy. It is the literal engineering blueprint of the model. And we can actually pull it up and read it for ourselves. In the world of AI engineering, there's a simple command called model.summary that works like an X-ray. It gives you a layer-by-layer readout of the entire AI factory, showing the precise shape of the data as it flows through the whole system. And here it is, the blueprint itself. Now, the Conv2D layers are where the AI is scanning for features, But look what happens right after each max pooling 2D layer. The spatial dimensions in the middle, they shrink, from 30 by 30 down to 15 by 15 and then to 6 by 6. But at the exact same time, look at the depth, that last number. It increases from 32 filters up to 64. That is the funnel logic, printed right there in the engineering summary.
This simple blueprint of scanning for features and then pooling the results to create a funnel, it's not just some theoretical exercise. It's the fundamental engineering principle that has powered some of the most famous and world-changing AI models in history. I mean, from the granddaddy of them all, LeanNet 5, which was reading handwritten checks way back in the 90s, to the total game-changer AlexNet in 2012 that kick-started the modern deep learning revolution, all the way to today's ultra-deep models like ResNet, they all follow this exact same core funnel logic.
So, when it all comes down to it, this entire incredible assembly line is designed to do one thing: to take the noisy, chaotic, high-dimensional data of millions of raw pixels and just distill it, step by step, down into one single, pure, abstract concept: CAT. That right there is the engineering genius of the funnel.
It really makes you wonder, doesn't it? If this one simple, elegant idea of the funnel got us this far, from reading numbers on a check to identifying almost anything you can think of, what's the next fundamental engineering principle that will drive the next generation of AI? What will the blueprints of tomorrow even look like?